Ladies and gentlemen, let's continue with Chapter 8 in the textbook of Cengel and Ghajar. We are busy with Chapter 8 on internal forced convection, and we are specifically busy with a section on laminar flow, the general analysis of it, and we've looked at the three very important boundary conditions of constant heat flux as well as constant surface temperature. Well, the last part that we need to do of developing of laminar flow in internal forced convection is to look at cases where the flow is still developing. So it's not fully developed, it is developing, and the necessary equations that we need to get for that. Now, this is an example of an equation in your textbook that was developed by Edwards in 1979. It is equation 8.62 in your textbook. Again, the fine print is very important. In your textbook, it doesn't show that it is the average value. However, in the sentence just before the equation, it exactly says that. And you have to distinguish that with equations where it might give you the value at a specific point. So just to remind you again, if we look at the Reynolds numbers as a function of x, then we will have the developing part and the fully developed part. So there's fully developed, and there it is developing. And you will also see this is for the case of a constant wall temperature. So that's the case for a constant wall temperature. If it's a constant wall temperature, then we know that the Reynolds number, if the flow is fully developed, should be equal to 3.66. And that derivation, or the most important part of the derivation, has also been shown in your textbook. So that value goes to 3.66. There it is. Now, in many cases, you're going to end up with a situation, because the flow takes so long before it is fully developed, that you might end up with a case where the total length that you consider is very short, or maybe it is approximately there. Then you cannot neglect this part of the Reynolds number, which is much higher. Now, for that, you can use that equation, so it would typically give you the average Reynolds number. But what is very nice is that, let's suppose your length is there, then it means it needs to integrate that and get the average over that part there. So that is that average. Takes into consideration the developing part, and it therefore do not give the value specifically at that point. If that was the case, then you will have to go and calculate the values for different x's, and you will have to do the integration. So that is a very convenient equation. What you will also see a lot that is going to appear now is cases where just the equation after this, it is going to give an equation where the Reynolds number, again it is the average Reynolds number, is something, it doesn't matter all the detail, but it will give terms like this. The viscosity bulk, surface to the 0.14. And that term is going to appear a lot. And typically, if you look at it in the text, it will say it is for high delta T's, high temperature differences. So what is this all about? It is about the fact that if that is your internal forced convection case, and that is the bulk temperature, so it means that the viscosity you're going to get will be based on the bulk temperature. Okay? So you're going to use the inlet and the outlet, get the bulk, and then you're going to get the viscosity there. However, in some cases, you need to get the viscosity on the wall. So that's the viscosity on the wall. And, they are using the surface, so let's rather use S for surface to indicate it is where it is the temperature at the surface, so there's the temperature at the surface. Now, many students would look at this equation and then they start using it because they are worried about this that needs to be taken into consideration, and in most cases, it wouldn't be necessary. So the question is, if that is the case, then, well, when is it necessary? Well, it's an engineering discretion decision. And the easiest is to look at that term, mu bulk divided by mu of surface. Let's suppose that ratio is equal to 0.9, okay, to the 0.14. And if you go and look at it, you will see it is 0.98. So at most, it can have a 2% effect on the Nusselt number. And then you can go and put in different values, and you will see even if you go down to 0.5 to the 0.14, then it will decrease to a value of 0.9. So it will have an approximately 10% influence on your Nusselt number. So that is what you need to do if you want to determine if the Nusselt number needs to be adjusted because of high temperature differences or high heat fluxes. Now take note, this equation is for a constant wall temperature. If you read carefully in your textbook, you will see there's something wrong there, there's something missing. And what is missing is there's no equation for a constant heat flux. Constant heat flux. Which is actually, should be the easiest of all. Well, the reality is, unfortunately, it is not so easy to determine that equation. It has been determined recently, and that equation can be written as the Nusselt number is equal to 4.36 plus a Nusselt number of the first part and a Nusselt number of the second part. And this is going to be equation 34 in the article, which is summarized there, and actually has an accuracy of 3.6%, and it is based on a database of more than 70,000 data points. The equation, unfortunately, this part and that part is a little bit long, so I'm not going to write it out here. I'm going to show you a little bit later where that is and where you can get it from. So that equation, and you will understand later on when I start doing the mixed convection part why we're doing that. So it shows that, firstly, this distance, LT, is equal to 0.12 Reynolds Prandtl diameter, and that value would then go to 4.36. And if you want to get the Nusselt number maybe at that point there, but not at that point, the average value from the beginning to the end, then you can get it from that equation. Okay, that is for laminar flow. Let's go over to turbulent flow. Turbulent flow is the next part of the work. And it has been summarized in your textbook in paragraph 8.6. Now, unfortunately, most of it is outdated. And I want to summarize it for you in terms of the following few slides. With turbulent flow and with laminar flow, one of the very important things are the friction factor from the Moody chart. The friction factor, which is being given as a function of Reynolds number, and then you've got a straight line like that. However, take note, it's a log-log scale. Okay. And then we've got the transition area, and then we've got the line of which epsilon divided by d is equal to 0, so that's the smooth tube, and then you get the results for the rough tube. So maybe there's epsilon of d divided by 0.01 or something like that. Now this graph is in your textbook at the end, in one of the appendices, and you are going to use it quite a lot. So take note of it and make sure you know where it is. This line here is the one for laminar flow. So that is equal to 64 divided by the Reynolds number. And there are some equations that you can use to determine that friction factor. There's simple type of equations. For example, you've already done it in fluid mechanics. The Blasius equation, 0.3125, Reynolds to the minus 0.25. So that is Blasius. Okay, take note, this is now for turbulent flow, and then also the Petikov equation, which works with the ln of the Reynolds number, which is the other equation, which is a little bit more accurate, that is also available that you can use. So that's the friction factor of the Petikov. Petikov equation. What I would like to advise you is there's going to be quite a number of problems in the tests and exams where we're going to ask you to determine the friction factor. Why? Because you need the friction factor to determine the pressure drop and also the pumping power or the fan power required. You can use any one of the equations. However, I always believe that when you use an equation, just go and check on your Moody chart approximately if it is correct, because it's so easy to make an error on a calculator if you're under pressure. Okay, now the very important thing that needs to be replaced is, if you go and look into history, there are so-called many equations that you can use and that has been used in this textbook. From simple ones to ones which are much more complicated. So the first one was a Dittes and Boulter equation, which was published about 90 years ago. That is based on experimental data that was collected approximately 100 years ago. The advantage of that equation is that it's a very simple equation. So when you're under time pressure, you can make use of that equation, and that is in many cases what happens in the tests and exams. And then that equation was followed up with a Colburn equation, and then the so-called Sider and Tate equation, and there you can see that term that appears of the viscosity divided by the viscosity on the wall. Okay? So specifically at high heat fluxes or high temperature differences, then that term is important. And then the last one was the so-called Glinsky equation, which was published in 1976. And there you can see the equation becomes much longer. However, it's a function of the friction factor. So you first need to go and get the friction factor before you can do the calculations. Now, when this work was done, and it was excellent work that these guys did, at that stage, the instrumentation wasn't as modern as we have today. They used thermometers with an accuracy of plus or minus 1 degree Celsius. Today, with thermocouples, we can get to 0.1 degrees Celsius. They used all primitive methods to determine mass flow rates. These days, we can measure it with Coriolis mass flow meters, very, very accurate, etc. But then, once you've done all the data analysis, you end up with something which we now have to do, and that is a so-called uncertainty analysis. Why? Because something like the heat transfer coefficient depends on the accuracy or the uncertainties again of the heat fluxes and the surface temperature measurements and your bulk temperature measurements, as well as the temperature differences between surface and bulk. So you end up in a situation where, let's suppose, you can measure the heat flux up to an accuracy of 5%, and your temperature differences has an accuracy of 1 degree Celsius, then your heat transfer uncertainties will be much higher than 5%. So that needs to be taken into consideration, as well as with the Reynolds numbers. Now, the result of that was that the equations that were used typically had accuracies of plus or minus 20%, and that was considered as quite good. Now recently, now at the University of Pretoria, we've been busy with this now for a long, long time, more than 10 years. We have many different experimental setups that we've built, and then decided later on now it doesn't work that well. And those were the students, Mother Stein, Kirsten Grote, and Nicole Coetzee, and then Dr. Marlies Everts, who worked on that for the past 7 years. And the result is that we've produced a new database consisting of 1,180 data points, of which we knew all of them, the accuracies and the uncertainties. And that made it possible for us to determine a new equation, and there they are, a simple one and then also a much more lengthy one. Now I'm going to show you in terms of the article. If you don't have anything to do, you can go and read through this article. But But the result is that we could do a curve fit through all the experimental data, and there you can see it, all the experimental data with a curve fit with an R square of 0.999. You'll see that there are some deviations there at high Reynolds numbers. There are two reasons for that. And the one is that the higher the Reynolds number becomes, the smaller the delta T's become. So the smaller is the difference between the wall temperature and the fluid temperature, and then your uncertainty starts increasing. And then the other reason for that is this is a log-log curve. So anything there looks like a big error, while actually on this side here it's a big error. That is a small error. But the important thing, and then okay, so this is what I want to show you. So what you have there is the turbulent flow regime. So the equations that we are going to discuss now and that I've given to you is valid only for the turbulent flow regime. Here you start going into the transitional flow regime. The transition, in terms of what I've referred to, where the flow changes from laminar to turbulent. So all those equations are given in an article that was published last year. All that detail, so we didn't show all the laminar flow details, but the bottom line is that in table 10, I know it is too small for you, but in that table, all the equations are summarized for the different flow regimes. You'll see the first few are for laminar flow, then for transitional flow, quasi-turbulent and turbulent. Quasi-turbulent and turbulent, those are the two important ones that you should take note of, especially for this part of the work, and then also for all the others. And then we've managed to put everything together as one equation. Okay, so we've put everything together as one equation. Now that would be a nightmare if you will have to calculate that on your pocket computer. So if you could put it in Excel or something like that, it's very easy for design purposes, because then you do not have to distinguish between laminar, transitional, and turbulent flow regimes. It will give it to you automatically. So it's very easy to get it from there. Right, let's go back to the equations. Right, there they are. Okay. So you'll see the first equation is given as a function of friction factor. You can use it like that, or if you then realize that the friction factor can be determined at this, you can do the substitution into it, and that is the result of the next equation, which is the Reynolds number is equal to 0.013, Reynolds to the 0.896, Prandtl to the third. The 0.867 you can make 0.9, especially if you want to make approximate calculations, and that equation has an accuracy of 6%, 6.4%. Okay. The next one, if you want to become more accurate, is that one there, and that has an accuracy of 3.4%. And there are all the equations, they are summarized, and I will give it all through to you so that you can take a look at it. Let's look at doing an example problem. In this case, we've got a tube and it is being heated at a constant heat flux. The inlet temperature is 20 degrees Celsius. It is water, and the mass flow rate is 12 liters per minute. The length is 6 meters. Outlet temperature is 80 degrees Celsius. The tube diameter is 25. It is well insulated so that there's no losses. And we have to determine the heat transfer rate and the surface temperature at the outlet. Surface temperature at the outlet. Now, I would always recommend that you draw a curve for yourself. Makes it more visually, and then it's easier to identify certain trends. Because it's a constant heat flux, it means that the inlet temperature to the outlet temperature is a linear increase. There's 20 and there's 80 degrees Celsius, and that is of the fluid. Now the wall temperature should be higher, otherwise there cannot be heat transfer, but we'll get to the wall temperature just now. So let's first go and get the properties. To get the properties, we normally use the inlet temperature and the outlet temperature. It's 20 plus 80 divided by 2, that's 50 degrees Celsius. If you go and look in table A9 in your textbook, the density of the water will be 988.1 kilograms per cubic meters. Thermal conductivity is equal to 0.644 watts per meter Kelvin. Cp is equal to 4181 joules per kilogram Kelvin. And the Reynolds number is equal to 3.55. Oh, and we also need the viscosity. The viscosity is equal to 0.504 multiplied by 10 to the minus 3 kilograms meters per second. And later on, as we do many of these types of problems, you will see that some things are sometimes convenient if you can go and calculate it before the time. For example, the surface temperature as well as the cross-sectional temperature as well as the mass flow rate in kilograms per second. So let's do that. The mass flow rate per kilogram second would be the density multiplied by the volume flow rate. Take note that V is volume flow rate. The density is 988.1. The volume flow rate is 12 liters. In terms of cubic meters, it is 0.012, and it's per minute, so per second, there it is. And then it gives us a mass flow rate of equal to 0.1976 kilograms per second. Cross-sectional area is pi divided by 4, d squared. It's pi divided by 4, 0.025 is cross-sectional area is equal to 0.004909 square meters. And the cross-sectional area, the surface area is equal to pi d multiplied by L. Pi, the diameter is 25. The length of the tube has been given as 6 meters. So the surface area for heat transfer is 0.4712 square meters. The heat transfer rate, very easy to determine. The heat transfer rate is equal to the mass flow rate Cp multiplied by the outlet temperature minus the inlet temperature. So this is equal to the outlet temperature, that is equal to the inlet temperature. The mass flow rate is equal to 0.1976. The Cp value is 4181, and the temperature difference is 80 minus 20. And that gives us a heat transfer rate of 49,575 watts. Okay. That's not an engineering answer. The engineering answer is 49.6 kilowatts. Okay. In all these equations, it's very important for us to know where are we. And what I mean with where are we, it is in terms of where do we are in terms of the flow development and if the flow regime is laminar or turbulent. For that, we need to get the Reynolds number, and there are two ways for doing it. We can say it is equal to rho Vd divided by the viscosity, or we can say it is equal to 4 times the mass flow rate divided by the viscosity P divided by the diameter. Now remember, this is only valid for a circular tube. Please remember that, and if you haven't written this, I would recommend in your textbook where that is given, you add this equation to it, but then you make the note, remember it's for a circular tube only. So for a circular tube, you can actually show it is equal to that. And if you use this equation, you'll see how easy it is. 4 times 0.1976 divided by the viscosity, which is equal to 0.504, multiplied by 10 to the minus 3, pi, and 0.025, and that gives us a Reynolds number of 20,000. The Reynolds number is 20,000, it means the flow is turbulent. For a circular tube, transition occurs at approximately 2,100 to 2,300, but then there is a region which is known as the quasi-turbulent flow regime, which is now between 2,000 and 10,000, but after 10,000 we can always say it is turbulent. Now, doing this is an option, so if you want to, you can calculate the Reynolds number from this equation also, but then you need the velocity. And mostly in engineering, the velocities are not given. You have to go and calculate it. Typically, we give things that are like the mass flow rates and the temperatures, the heat transfer rate, but normally we do not give the velocity. How can you calculate the velocity? Well, the volume flow rate is equal to the velocity multiplied by the cross-sectional area. So from this, you can go and calculate the velocity, which is equal to 0.4074 meters per second. Then you can put it into that equation, and you should get the same Reynolds number. Right, since the flow is turbulent, there we can see all the options that we have. The easiest one is equal to 0.013 Reynolds to the 0.867 multiplied by Prandtl to the third. That's already accurate to 6%, so that's fine. Nusselt number is equal to 0.013. The Reynolds is 20,000 to the 0.867. Prandtl is equal to 3.55 to the third, and that will give a Nusselt number of 106.3. The Nusselt number is equal to HD divided by K. It's equal to the Nusselt number. The heat transfer coefficient is what we would like to determine. The diameter is 25 millimeters divided by the thermal conductivity, which is equal to 0.644. It's 106.3, and that will give us a heat transfer coefficient of 2737 watts per square meter degree Celsius. Right, now that we've got the heat transfer coefficient, we can calculate the temperature at the outlet. Oh, okay. Before we do that, sorry, I forgot. When we got the Reynolds number of equal to 20,000, let's just go back to the sketch. This is 6 meters, so the tube diameter is 25. So because it's turbulent, it means that it will only be 250 millimeters before the flow is fully developed. So there's 250. So for all practical purposes, the heat transfer coefficient there would be a little bit higher, but after that it would be fully developed. Now this 250 millimeters in terms of the total length of 6,000 millimeters is less than 4%. So therefore, we are going to consider the flow as fully developed right through. And if it is fully developed, then it means this heat transfer coefficient is constant and the delta T is constant, as we've done in this work. So we know that the wall temperature should do something like that. Maybe it doesn't look parallel, but it's parallel to that line, so the delta T is constant. So we can say that is equal to the temperature at the surface at the outlet. This is the temperature at bulk. This temperature, then we can say, is the surface temperature at bulk, and this is, that temperature there is the surface temperature at the inlet. So now that we've got the heat transfer coefficient, we can actually determine the wall temperature. It's equal to the heat transfer coefficient multiplied by the area multiplied by the temperature at the surface outlet minus the outlet temperature of the fluid. The heat transfer rate we've determined as 49,575. It's equal to the heat transfer coefficient, which we have just calculated, 2737, multiplied by the surface area for heat transfer is 0.4712, multiplied by the surface outlet temperature minus the outlet temperature of the water, which is 80. And that would then give us a surface outlet temperature of 118 degrees Celsius. So this temperature here is 118. So therefore, delta T, which is equal to the surface temperature at the outlet minus the fluid temperature at the outlet, is equal to 118 minus 80, and that is equal to 38 degrees Celsius. So the delta T is 38. And once we know the delta T now, which is 38, it's very easy to determine the surface temperature at bulk, which should be 50 plus 38, which is equal to 88 degrees Celsius, and the surface temperature at the inlet, which is 20 plus 38, which is 58 degrees Celsius. So there's the wall temperature at 3 different positions. But of course, you can go and calculate it anywhere now that you want. But now everything is known. Ladies and gentlemen, any questions? Okay. So we are at the end of this chapter now. However, there is another part that I'm going to add. So with the next lecture, I will start on that, and that is the part on mixed convection, which is not in your textbook yet. It will be in the new textbook that will appear at the end of this year, that will be printed. But I want to refer you to 5 or 7 examples that I've done previously, and which are all worked out on YouTube, and I've given you the URL. So it was while I was on a sabbatical, I've worked out those problems, and I've done it on a big piece of yellow paper, all in detail. However, the very important thing that you need to remember now is when the flow is turbulent, where previously we worked with Sider and Tate, Dieters and Bolter, the Glinsky equation, etc., then you need to replace this with the Meyer et al. Equation. Okay, et al. Just means that you're not going to name all the authors because there are more than 2. So that is in 2019. And that article was actually now published on Saturday evening. So it has been very freshly been printed and made available, and it's open now to the public. So in 2015, ladies and gentlemen, if I can give you a hint, do not go to the test or the exam if you didn't work through that. I would recommend that you do not just play the video, start the video and see what the problem is, then you work it out yourself, and then you compare it to what I've done. Of course, the Nusselt numbers that you're going to calculate in case of turbulent flow might vary a little bit, but you'll see the differences will not be 20 or 30 or 40%. It will not be that large. It might be 10 to 20, but that would be at most. Right, ladies and gentlemen, if there are no more questions, then I will see you again with the next lecture. Thanks very much.